Let's do example 2 where it talks about the amount of caffeine in a person's bloodstream after drinking a cup of coffee. Okay, so it says, what is the initial amount of caffeine when no time has yet elapsed? Well, when no hours have gone by, there are 180 milligrams of caffeine in this person's bloodstream. Just drink it or ate it, chocolate. Took it as a pill, who knows? Write a ratio comparing the remaining amount of caffeine in the bloodstream to, is that one word or two? To the amount there was an hour before. There should be 7 ratios here. Ooh, yeah. Okay, here we go. Let's get them all 7 of them. So the first ratio, the caffeine to the time. Okay, so here's what I see. Or, oh no, not caffeine to time, caffeine to caffeine from the hour before. Okay, so here's our ratio, 144.0 milligrams as a ratio compared to 180.0 milligrams the hour before. Got it. And then, okay, 115.2 milligrams as a ratio to 144.0 milligrams, 1, 2, okay, 92.2. Okay, I think I'm going to start getting a little bit lazy with the milligram labels right now. Here we go. 73.7 to 92.2, 59.0 to 73.7, 47.2 to 59.0, 37.7 to 47.2. Okay, that's a lot of them. Got it. 1, 2, 3, 4, 5, 6, 7. Got it. Rewrite each ratio as a unit ratio. What do you notice? Okay, here we go. So I'm going to clear this out from the last one. 144 divided by 180.8. Okay, so this, if you simplify it, that ratio is 0.8. 115.2 to 144.8. Oh, biscuits. Is this going to happen all the way across? 92.2 compared to 115.2. What happened there? Huh. But it's really, really close to 0.8. So I'm going to round it. Approximately 0.8. Pretty darn close to 0.8. Next one, 73.7 to 92.2. Oof. Just under, but also really, really close. 0.0007-ish away. That's pretty close. So I'm going to also write approximately 0.8. That would round to 59 compared to 73. Oopsie, 0.7. Just a little bit over, but also approximately 0.8. Round it to 0.8. 47.2 compared to 59. A solid 0.8. Let's see. 37.7 compared to 47.2. Also pretty close. Not exactly, but approximately 0.8. Oh, so each one of these ratios, if you go down, oof. Okay, so what's cool about this is here's what I see then. If this, so notice that if I take 180, multiply it by 1 or 0.8, I get 144. What kind of pattern is this? I see a constant multiplier. 144 times 0.8, 115.2. That 115.2 times 8, 92.16. So it got rounded to 92.2. Okay, 92.2 times 0.8, 73.76. Oh, but I bet you they used 92.16 times 0.8. Look at what is happening. Yeah. So it's just that they keep rounding. That's why there was a little bit of an approximation. Yeah. So it looks like there is the pattern. Huh, and that constant ratio right here of one to the other was also supplied us with a constant multiplier. Oh, what type of pattern is this? So I have to go back and think to myself, is this linear? Is this inverse variation? So this pattern is not linear. Okay, because it wasn't +6 +6, or I'm sorry, minus, oh, wait a minute. What is 180? Take away 144. 36. It wasn't minus 36 minus 36 because 144 minus 36 would have been 108. And then minus 36 again, 72. And that is not the pattern it followed. So it is not a constant subtraction. So it's not linear. And it is also small, big, small, big, small, big. It never does the inverse where it's big over here and small over there. That doesn't happen. Wait a minute. Small, big. That's big or smaller? It could. So it's definitely not linear. Possibly. Oh. Possibly inverse based on what I was just talking about, because really this is small to big, and then this is bigger, and that is getting smaller. So if we kept doing this, this would get bigger and that would get smaller. But I noticed that this happens. So there's an initial value here that actually has a point when it's 0, and with inverse variation, right, we would have something like caffeine is equal to some constant K over the number of time, but we can't divide by 0. So at time 0, we wouldn't be able to do this. So, not inverse variation. So then we go back to what happened in the last one when we were looking at bacteria, and that was double, right? Had a constant multiplier, and we ended up rewriting it with exponents. So here we go. Multiply, if you do repeated multiplications, this is going to be exponential due to repeated multiplication. Yes. All right. What is the initial amount of caffeine when no time had elapsed? But we had already written down, this is a duplicate question. Accident. Okay, so we know that this is exponential as well because it has repeated multiplication. Let's write down what it takes to be an exponential function. And so when I think about an exponential function, I think, okay, this is there's f of x for your function notation, or if you prefer y, there it is, where it is a times b to the x, where, or if you prefer, I would say this is the response variable, or the dependent variable. Oh man, I want to use a whiteout. Okay. Yep. This was the initial, like in the bacteria. So back in this example, right, we had 6, which was the initial amount, and then that was the repeated multiplier. So here, so the response variable, or the dependent variable, is equal to the initial, okay, times, and this is the constant multiplier to the explanatory variable. I had to squeeze it in there. Maybe I should have written that whole thing here. That's okay. But I wanted to write down where, make it really explicit. A is the initial amount, and B is the constant multiplier. Okay, or in other words, it also appeared in the last example as the constant ratio of new to old. Okay, so if you're ever like, I can't find the constant multiplier, how do I find it? When it's funky like a decimal, you have to do a new to old scenario, and they have to just be like differing by maybe 1 year or 1 increment. Okay, so there is our model for this. So let's look at another scenario where it's line versus exponential. Fill in the table based on this pattern. Oh, I see it. Times 3 times 3 times 3. So all right, here we go. 54 times 3, 162. 162 times 3, 486. If I'm going the other way, I would be dividing by 3 or taking a third, because I need to be portioning now instead of scaling up and tripling. So 2 times 1/3, right? Math back. 2/3. Or if you did 2 divided by 3, you'll get the same shenanigans. Turn that into a fraction. Yeah. So 2/3. Okay. What if I do it again? 2/3 divided by 3. 2/9. Okay. Do it again. Answer divided by 3. 2/27. Got it. And if you triple all the way down, it will work out. What is, oh, I have to graph the values. Come on now. Don't forget to follow instructions. 0, 2. So hold on, just 0, 2, 1. Right 1 up 6. 1, 2, 3, 4, 5, 6. Right 2 up 18. What? Wow. That is big. Okay. I don't like it. So here's what I'm going to do. I'm going to decide that these axes are not working for me. And this is going to happen, you know, we don't have a rule that says I have to use those. So I'm going to make my own bold. None of this goes below 0. So here, I'm going to put this as my x-axis. And I don't know, I'm kind of okay with this happening because we're going into positives and negatives here. So this is cool for my, but I don't need a lot. So what if I go like 1, 2, oopsie, my bad, 3. And so that would mean -1, -2, -3. Okay, it leaves off a couple, but that's all right. And this one, since we go up to 3 and 3 is 54, it really should either count by 2s or count by maybe 2s. So 2, 4, 6, 8, 10. 12, 14, 16, 18, 20. Okay, there. I modified this graph to fit my actual needs. So I'm cool. 0, 2. So that's there now because I'm counting by twos. 1, 2, 4, 6. So 1 to the right, up 6, 4, 6. 2, 18. 2 to the right, up 18. 2, 4, 6, 8, 10, 12, 14, 16, 18. Got it. This is off the charts. Fine. -1. So 1 to the left and 2/3. But no, remember this is actually 2. So 1 would be 1/2. So there. -2 and 2/9. All right. So it looks like our graph is curving up like this, but it doesn't look like it's ever going into the negatives. So I don't go below this boundary here, down. I don't go below it. I just get close to it. Okay. Right on. What is the initial value of y when x equals 0? 2. Also known as the y-intercept. What is the pattern? Find the constant ratio. The pattern, so the constant ratio, which we said was going to be called B for this one, so the pattern is triple. Constant ratio means that the constant multiplier, or the B for this model, is 3. Triple, triple, triple. Write an equation for this pattern. Okay, well, look. It says the response, which is y, is equal to the initial amount, which was 2, right there. Initial 2, and times the constant multiplier, which was 3 in this case, and to the explanatory variable, which is just what's keeping track of the counter here, but that is x in this scenario. As the input x's get more and more negative, what happens to the output of the y's? Well, here's what's up. As x gets more negative, the y's get closer to 0. Like these are turning into tiny fractions, tiny portions. But never become 0 or negative. Okay, so as the x's get more and more negative, these fractions are getting tinier. They're getting closer to 0, but never are 0 and never become negative. Will there ever be an x that gets us a y value of 0? No. Near. But will never actually be 0. So it rounds to 0 eventually. But that's only when you're rounding. And if we took something in this case, you know, like, and we're doing this divide thing where it's just 2 divided by blah, 2 divided by blah, 2 divided by blah, 2 divided by big number never turns out to be 0. Yeah. Never. Okay, so eventually it'll be close, but it'll never be, and it rounds eventually, but that's a choice of the person computing. Okay, so let's do number 2 of example 3. It says, fill in this table based on this pattern. Okay, so the last one was times 3 times 3 times 3. But I feel like this one is 2 plus 3 is 5. 5 plus 3 is 8. 8 plus this is plus 3. Oh, I like a plus 3. That's 14, 17. How much plus 3 gets 2? Negative 1. So now I'm kind of subtracting 3. Negative 4 plus 3 makes 1. Negative 7 plus 3 makes 4. Okay, sweet. Fill in the table based on the pattern. If you're going down, you're adding 3. If you're going backwards, you're subtracting 3. Done. I see positives and negatives. So I'm going to keep the axes where they are. And what does that mean? What will these plots look like? Also feels a little weird to just have X and Y and not an actual variable. But anyway, 0, 2, done. 1 to the 1 to the right, 5 up. 1, 2, 3, 4, 5. 2 to the right, 8 up. 1, 2, 3, 4, 5, 6, 7, 8. Okay. 1 to the left, 1 down. Done. 2 to the left, 4 down. 1, 2, 3, 4. Got it. 3 to the left, 7 down. 1, 2, 3. 1, 2, 3, 4, 5, 6, 7. Okay. They are definitely lined up. So, oh boy. Come on, Abby. Here, I need to use my old notes page. There. Ay, caramba. My ability to make a straight line. Yeah, I needed a straight edge. Look at how far off I was. That's okay. Please ignore the accident. What is the initial value when x equals 0? There is the initial value. It was 2, just like before. What is the pattern? The pattern was plus 3. So constant plus 3, which means it's linear. And find the constant ratio. Nope, it's not a ratio. It was a constant rate of change, but it's a plus 3. So I guess you could say the constant ratio, the ratio, I mean, slope is a ratio, right? And that is the change in response compared to the change in explanatory, or the change in y variables, or the dependent y compared to the change in the independent x's. Okay, but even if we do that, how did that change? Yeah, it went up by 3. How did that change? Yeah, it went up by 1. Constant plus 3. Okay, but that in this case is called the slope because it's linear, right? A pattern for this one. An equation for this pattern, I mean. So I see y is equal to the initial, because the, oopsie, I guess I'll do that. That's what happened in my brain. I couldn't do it 2 steps. The initial is 2, and 3 is added x times for every time you increase. Okay, so remarks. Let's write down some things that I think are remarkable, like the difference between these 3, this model, and even the inverse model. Right? Where did I have that one? Okay, so I have a copy of my inverse model. Yeah, okay. Everybody got it. Versus that one? Okay, so here's what I mean. Just visually speaking, here's a line. Here was the inverse variation, and here is the exponential model. Yeah. And we also saw another exponential model graphed right here that went down instead of up. Okay, so let's make a remark about a comparison between these visualizations. So first things first. Lines have no curvature. Lines have no curvature in their graphs image without, okay, there's, and they have model. They model with, let's see, response variable is equal to the initial plus the constant change, constant addition or constant subtraction times the explanatory, or y equals b plus mx. Okay. What about the inverse model? Yeah, so that picture had curvature. So let's see. Inverse variation have curvature with two boundaries. Two boundaries that they don't cross is what we saw. Two boundaries they don't cross. Okay, and they model with response variable is equal to constant k over explanatory variable. Or if you want to rewrite that, y equals k over x. Okay. And if I'm just, I'll draw my pictures down here maybe, or to the side. And then exponential curve. So exponentials have curvature with one boundary, or okay, thing that it doesn't cross. With one boundary, it doesn't cross. They model with the equation response variable is equal to the initial times the constant multiplier to the explanatory, or y is equal to a times b to the x. Okay, and now I'm going to go ahead and just make a quick sketch, right? You know what? Let's make the axes black and then the graph here. So there's a line. Yeah. And this would be like the initial, and then it would do its thing. Let's see. Inverse variation has two boundaries. Its graph has curvature, but doesn't cross across boundaries. And then exponential, and we've seen two exponentials so far, actually. So I'm going to make two separate graphs right here. Okay, both of them only having one boundary. In the situation we just saw, it went like this. So it had curvature and it went up, and it had one boundary that it never crossed. And then in the caffeine, the bloodstream one, it came down because it was getting less and less caffeine in the bloodstream, but it also had a boundary that it never crosses. Okay. So let's give these boundaries a name. You know, we said it gets closer and closer to zero, but it never becomes zero. And that has a name. It's called an asymptote. So an asymptote is a boundary. It can never be crossed. This is a steady boundary, like saying no to someone. Should be respected, where a list of values approach the amount of the boundary but are never equal to the amount. And so never crosses that boundary. That's an asymptote. In this class, this is a good enough definition. And also in Math 95, I want to say that the examples that we're going to see in this class, those boundaries are always the axes, but that is not the case in future classes. So if you either jump tracks into the sciences, or you go on to Gen Ed Math and maybe they have a different model, this could move around in space. Like that boundary might be different. But so here's what we're working with. And in this particular section, we're going to focus on this model.